The LI for this lesson is to be able to use differentiation to solve kinematic problems. Now, we know that the gradient of a displacement time graph shows the velocity. And if the displacement is expressed as a function of time, then the velocity can be expressed as the derivative of the displacement with respect to time. So velocity is ds over dt. And that makes sense because we know that speed, or velocity, is displacement over time. So velocity is the change in displacement over the change in time, the derivative of the displacement with respect to time. So that's our first important formula. We also know that the gradient of a velocity time graph represents the acceleration. And then in the same way, therefore, acceleration is equal to the derivative of velocity with respect to time. Now, because velocity is equal to ds over dt, we therefore know that the acceleration is the second derivative of displacement. So d squared s over dt squared. And so what we need to be able to do in this chapter is move easily between displacement, velocity and acceleration using these facts. So if I've got displacement, so if I know the displacement of something as a function of time. So for example, I know that s is equal to t squared plus 7t or something. So some sort of function of time going on there. If I want to get the velocity, so I want to get v as a function of time, I need to differentiate. So to get from displacement to the velocity, I differentiate. Then to get to the acceleration as a function of time, so a as some sort of function of time, I just need to differentiate again from the velocity to the acceleration and differentiating. And we'll see, sneak preview of what's going to be coming from future lessons, how we can go back up using acceleration. But for now, we're just focusing on if I want to go from displacement to velocity, I differentiate, and then to get acceleration, I'll have to differentiate again. So if we look at this first example, particle P is moving on the x-axis at time t seconds. The displacement is x meters from the origin is given by x is equal to t to the power of 4 minus 32t plus 12. So what they've given us is they've given us the displacement. And for some reason they've decided to use x rather than s, but that's fine. They've given us x as a function of time. And part A is asking for the velocity when t is equal to 3. Well, clearly I'm going to be plugging t is equal to 3 into something, but I've not got an equation for the velocity yet. I've only got the displacement equation. So first I need to get that velocity equation. So I want to get v equals, and I'm going to get there by differentiating down. So if I'm going to have to differentiate the displacement to find the velocity. So let's do that then. So I know the displacement is equal to t to the power of 4 minus 32t plus 12. And I want the velocity. So the velocity is the derivative of the displacement with respect to time. So dx by dt. So I just need to differentiate this. And these should be nice and simple differentiations compared to the hard ones that you've seen in pure. So I've got 4t cubed minus 32. There's my velocity formula. So that is velocity as a function of time. And I want to know the velocity when t equals 3. So when t equals 3, the velocity is going to be, well, just sub 3 straight in there. 4 lots of 3 cubed minus 32. Let's do that on my calculator. 4 times 3 cubed minus 32. 76. So at t equals 3, the velocity is equal to 76 meters per second. Okay, then part B says the value of t for which p is instantaneously at rest. Well, this is similar to some of the examples we did last lesson. If p is at rest, that just means that the velocity is equal to 0. So I want to know when the velocity is 0, what is t going to be? So I'm going to sub in velocity of 0 is equal to 4 4t cubed minus 32. So I get that 4t cubed is equal to 32, t cubed is equal to 8, and then that means that t is equal to 2 seconds. So at t is equal to 2 seconds, that is when p must be at rest. And then finally for part C. Part C is asking for the acceleration of p at 1.5 seconds. Well, we haven't got the acceleration yet, but we know how to get it because we've got the velocity now. So if I want to get down to the acceleration, so I want a as a function of time, and this was a function of time, I didn't write it in earlier, then all I need to do is differentiate the velocity. So to go from velocity to acceleration, I'm differentiating. So let's do that. So I've got c. Acceleration is the derivative of velocity with respect to time. Remember, the velocity is, let's just write the velocity above here. Velocity was 4t cubed minus 32. So I've got 12t squared, and that's it. The acceleration is 12t squared. So when t is equal to 1.5, the acceleration is just 12 times by 1.5 squared. And that's 27 meters per second squared. So I've shown really easily how we get from displacement to the velocity and then to the acceleration. So after that example, you should be able to have a go at exercise 11b.